So when we were talking about a function, f of x comma y, we could talk about the level curve, meaning you're talking about z equals something. You're creating these sections that go all the way through, and we would get some sort of 2D curve. So 3D surface, you slice it, you get a 2D curve. Now I've got some four-dimensional thing. If I were to slice this and put this function equal to maybe c equals 3, so if I've got f of x comma y comma z equals 3, I've got 2x plus y minus z squared plus 4 equals 3. So if you want to make it look more standard. So again, four-dimensional thing, can't really think about it. But if I take some section, then I've got a 3D surface. I'm going to give you 2 seconds. Level surfaces. I've got some four-dimensional thing, can't really think about it. But if I let my W, or my output, equal 1, it's just asking me to describe what we're going to see, what now three-dimensional thing would we see. So if I slice through and let W equal 1, what kind of surface do I see here? Next one, I let W equal 5. So before we were looking at level curves. So we had a three-dimensional surface. And we were able to kind of imagine this by drawing 2D level curves. So we're slicing it z equals 1, z equals 2, z equals 3. If I'm standing at this point, if I head in the direction, so like directional derivatives, in the direction of 1 comma 1, then is my function increasing or decreasing? Increasing. We're looking at these level curves here, 1, 2, 3, 4. Z equals 1, so I'm ascending. So if I head in the direction of 1, 1, I'm increasing. One of the things that's true about our gradient vector, we said it points in the direction of steepest ascent. That gradient vector is always perpendicular to the level curve. So if I want to head in the direction of steepest ascent, you're going to head in the direction that you are perpendicular to that level curve. So you can just kind of put different points there. And you see, like, oh, well, if my z's are increasing as I go out, if I want to head in the direction of steepest ascent, I'm just going to draw a perpendicular vector. So again, we had some sort of function. We were just picking different values of z, and we would get a 2D image and then sketch it. And it was a way to kind of look at this contour map of what's happening by shrinking it down to 2 dimensions. Again, you can't visualize a 4D thing. However, you can kind of say, oh, well, if I look at different level surfaces, imagine this one over here, and go, oh, well, if I let W be different things, my level surfaces now are going to be 3-dimensional shapes. And really what I'm trying to accomplish in this picture is your gradient vector is still going to be perpendicular, but now to the surface of your level curve. And with that, we are all set for content for our second exam. So really, if we take a step back and kind of think about the questions that we can be asked, the question types are actually identical to what we were asked before. But maybe by the time we pull it to the exam and it wants us to compute, partial derivatives, maybe it's just not a function of 2 variables. Maybe it's a function of 3 variables. You can still compute partial derivatives. You can compute mixed partials. Maybe I want a gradient vector. We can just have multiple variables now, and you're just going to go x component, y component, z. All right, got some practice problems. Take a second. See what we can come up with. So here's on the projector, here's your visualization for a four-dimensional function. So we said, now you're going to input a point in 3D. So now your input is the 3D location, and you can assign meaning to it. You can say it's a temperature. You can assign a color to it, and they're actually assigning color to mean something here. Think of the dark red values as being like a high temperature or high value of the output. You can think of like the blue as being like a low value. So you can still visualize a four-dimensional thing, but it's not going to be as straightforward as when we were going to 3D. So again, if you want to think about a gradient vector, it's now a 3D vector that points in the direction of steepest descent. Greatest increase for the function. So again, if you're thinking temperature, maybe it's pointing directly towards the heat source. So the gradient points to the maximum rate of change.
So they're negative?
Yep. You're going to find the gradient vector. If you have the negative of the gradient vector,
Is that like, when you give the example, when you walk down the negative?
yeah, so if I'm walking in the direction of steepest descent uphill, you're going at minimum. one's not too bad. It's just making sure that we've seen this stuff before. Yeah, I can give you a function with now 3 different inputs. You now plug in a 3D point, you get it out.
Question with that, how do we know not to take the first derivative when it's already been taken?
It doesn't want a partial derivative. It just wants the output. It's just saying find the output of the function. The
Okay.
W value.
Evaluate, gotcha. Okay.
The second one says compute all first partial derivatives. So now you can have a partial derivative with respect to x, with respect to y, with respect to z. And you can still use this notation. Totally fine. I'm going to treat all of my things that have x as the variable, everything else as a constant. So this would be 4x. E to the y comes along to the right. Nothing else has an x, so it all drops. So now taking the derivative with respect to y, y is my variable, e to the y, or derivative of e to the y is e to the y. 2x squared comes along, everything else is. Partial derivative with respect to z. Now I've got a chain rule here. The derivative of cosine is negative sine of 5z times the derivative of the inside, which is 5. Just cleaning that up, you could have just called it 5 sine of 5z.
Now, would you write the answer as the gradient g parentheses x, y, z?
No, so here if it says just compute the partial derivatives, you're kind of thinking of them
Independently,
If it
okay.
asks for a gradient vector, you're absolutely right that it's just a vector with x, comma, y, comma, z. But if it's just saying compute the partials, you can think of them as their own thing.
Yeah, okay, okay.
3, determine the minimum rate of change. So I said, okay, well I know that the maximum rate of change happens in the direction of the gradient vector. So that means that the minimum rate of change is just in the opposite direction of the gradient vector. So compute your gradient vector, partial x, partial y, partial z. So now by finding the gradient at the point that they told me, 1, 0, negative 1, this now points in the direction of the maximum rate of change. Which again, let's just kind of pause and think about this. This is saying you're standing in a room. Again, you can think of this as the temperature example. When you go to the point 1, 0, negative 1, if you head in this 3D direction, that will point in the direction of maximum ascent. Well, if you want the minimum, it's just going to be in the opposite direction, so the negative of your gradient vector. Now it also says what is the minimum rate of change. It is just the magnitude of that vector. And I did forget something here. This needs to be negative here. Your minimum rate of change is going to be a negative. Or describe the level surface. Can't really think of this 4D thing, but if I slice through with a W value, in my head, I just picked let W equal 1. Just going to be the easiest value for me. So now if I think about x squared plus y squared plus z squared equals 1, that all my level surfaces are now just going to be spheres centered at the origin. Here, if I plug in W values greater than 0, so again, I'm just going to pick 1. X squared plus y squared minus z squared equals 1. Honestly, that's a flip through the notes, look at that reference sheet again, and we go, okay, well, this would have been a one-sheet hyperbole. All right, let's talk about 6 together. So this function t of XYZ measures the air quality on a scale from 0 to 100 of a room that someone has just smoked a cigarette. X, Y, and Z are measured in feet from the center of the room. So the origin, 0, 0, 0, is the center of the room. You tell me where in the room you are, and it's going to output the air quality. So this is not asking us to compute anything, but just interpret what would the gradient vector of this coordinate, what does this mean here in the context of this cigarette?
If you're at that 2 feet, 3 feet, 4 feet from the center in the room.
Yep.
And you move towards that direction. And
The
you're
first
getting
often.
worse the fastest.
Say,
Then you're getting the worse air quality the fastest. Because that's the gradient vector.
on a scale from 0 to 100, let's think that 100 is a good thing.
Oh.
So you're heading in the direction of the cleanest air. It all just depends on how you, and I'll probably rewrite it to think 100 means good.
It's in a way.
Okay.
So again, you're standing at this point. If you head in the direction 4, 2, 1, you're escaping. You're heading towards the best air quality the fastest. So heading in the opposite direction, or the negative of the gradient vector, you're heading kind of right towards wherever that person smoked, probably. Now the next one is just asking us to interpret the magnitude of that vector. What does this say?
Could be the speed at which you're going in that direction.
Yep. So heading in that direction increases the air quality by 2 points per feet. So our function's measured in points on a scale from 0 to 100. So we are increasing our air quality by 2 points for every foot. All right, just passed around the very first practice test for exam 2. Remind me, I can't remember how we reviewed last time. Did we kind of split up and then talk about it, or did we do it together? And then, of course, how do you want to do it?
I think we did it on our own, and then asked for help after and afterward.
Is that how we want to do it again?
Yeah.
All right, this is the first practice test. This one should feel, quote unquote, the worst. So if we're still shaking off some rust, don't be discouraged. first one is just computing all three partial derivatives. So I've got partial with respect to x. And I remember my Calc 1 derivative that says that the derivative of square root of something is the derivative of the something over 2 root something. So you can think of that as 1 over 2 times the square root of whatever's in the inside, times the derivative of the inside with respect to x, so 2x. Or you could recognize that as, oh, it's just, derivative of the inside over 2 times the square root of the inside. 2's cancel out, so I get x over square root of x squared plus y squared plus z squared. And I realized, oh, kind of the same problem. The next one, now I do the same thing with y. So I get 2y over 2 times the square root of x squared plus y squared plus z squared. Last one I realized, oh, it is the same. So 2's cancel out. I get z over square root of x squared plus y squared plus z squared.
Keep them, the x and y and z separate again. You don't write them in like a vector form.
Yeah, so again, if it's just asking for the partials, you can write it as its own standalone thing. The next one says, determine whether the function is increasing, decreasing, technically this should say or neither, in the direction of this vector here, at the point 2, 1. So this is getting back to the idea of a directional derivative. So this is saying, compute your gradient vector, and we know our directional derivative ends up being the dot product of your gradient vector and the direction vector. So my direction vector, I just wrote it in brackets, is 1, -1. My gradient vector is partial x, comma, partial y. The gradient vector at the point 2, 1, plug in 2 for x, 1 for y, is 4, 4. That's saying if you head in the direction of 4, 4, you're going to go in that direction for greatest descent. But here it's saying, well, what happens if I travel in the direction of 1, -1? Well, the dot product of those two vectors gives you your directional derivative. So thinking back to exam 1, dot product, multiply the 2 x's, multiply the 2 y's, add them together. Here I get 0. So I can say neither increasing nor decreasing as the directional derivative is 0. If I had gotten a positive number, the function would be increasing. If I had gotten a negative number, the function would be decreasing. Questions on the first page? Yep. And yes, I will post the solutions.
Just the directional vector is 1, -1 because your I is 1 and your J is -1.
Yep. And that's just given to you. It's not always that dimension. critical numbers, classify each point as a local max, local min, or neither. We gotta think back. What do I need for this problem?
This one's for this one?
Say again?
You use this one for this one? The table?
You need a reference sheet. You need the second derivative test. That was the one that was talking about the discriminant. It had some sort of formula, so we'll flip through the notes. We want to find the quote-unquote second derivative test.
Second derivative test. I don't.
So just to remind us, second derivative test was talking about your second partials. So we plug the point into this quick formula. We basically get two outcomes. If this discriminant is a positive number, then you have a relative extrema, meaning you have a max or min. If you get a negative number, it just means it's a saddle point. That means you lived on the perimeter. So when you go and travel in one direction, you're at a minimum. But if you travel in the other direction, you're at a maximum. So that privilege. If your second derivative for either x or y is a negative number, think concave down, then you get a maximum. If your second derivative is positive, so think concave up, then we get a local minimum. Inconclusive. So here, I didn't have to compute anything. We've always seen this where you have to take all the partials. Here it was just nice, it gave us all of this information in the table.
Okay, nice.
So my discriminant well, first, what are the critical numbers looking at this table, and how do you know? Algebraically, how did we find critical numbers?
I had to set the first derivative to 0.
Yep. So it needs to be true that both your partial with respect to x, both your partial with respect to y, those two things need to both be 0. So at the point 0, -1. This is a critical point. Because my partial with respect to x is 0, my partial with respect to y is 0. So this is a critical point.
And you're saying they're both 0 in the second and third column?
You don't pay attention to the column.
Right.
So, yes, I agree that is what I'm saying, but the partial with x is 0, the
Right,
partial
okay.
with y is 0.
Yes.
Now, if we're looking at this one, the partial of x is 0. So if you travel in the x direction, you're not increasing or decreasing. But that's not true for the y direction. To be a critical point, both have to equal 0. So f sub xx f sub xx is negative 2. F sub yy is 3. F sub xy is 2. Now, what should f sub yx be at this one?
2 as
Also
well.
2. They're the same.
Yeah.
Your mixed partials are equal.
And they're not the same when you did something wrong.
You did something wrong, right? So going back over to just my reference sheet, that's on my page of notes that I'm allowed. I got a negative number. If your discriminant is negative, that's neither a local max or a min. That is our quote unquote salad. Next one, number 4, still just comes from the reference sheet. I would just take 2 seconds, flip through your notes. It's asking me to convert a point from rectangular to cylindrical coordinates. So I'm just going to go through and find my reference sheet for cylindrical coordinates. Negative square root of 3 over negative 1 is just square root of 3. So I'm asking myself, where on the unit circle is the tangent, meaning the y coordinate divided by the x coordinate, square root of 3?
Pi over 3.
I agree, but not entirely. But yeah, we need to think about what
Because
quadrant.
both of them are negative. So both of them are negative in the third quadrant. Is it the third?
Yeah.
Yes.
So on your reference sheet, whenever you see that theta,
Add 180.
just add like a little asterisk there to remind yourself, like, you need to think about the quadrant that we're living in. And pulling up my unit circle.
Right. Where is it? So it's not pi over 3.
My coordinate here is negative 1, negative 3. That's in the fourth quadrant. So it's that whole idea of add pi. Yes, you could say 180, 40 degrees. So the quote-unquote over 3 in that quadrant is 4 pi over 3.
Nice.
we said that we love the z
The
coordinate.
Z is just Z.
Z is z.
Okay.
Did not matter what hideous number we got. Z is z. Question. Velocity of a fly moving through the room is given by v of t. This is a vector value function. So this is one of the first things that we talked about. So now this is a function. You give me a t value. It's going to output a vector. In this case, it outputs a velocity vector. If the fly had a position of 5, 3, 2 at t equals 0, the question says determine the z component of the velocity vector at t equals 3. So just, we got to unwrap exactly what is it saying here.
Yeah, that's B of T. So B of T is position.
Velocity.
Velocity
So your first derivative of position.
Okay.
So it's already the derivative.
Already derivative. Okay.
That would give you the velocity vector.
So
The z component of the, oh, hang on, wait. I need to
rewrite that a little bit.
Of the position vector,
Okay.
not of the velocity vector, of the position vector.
Okay. Determine the Z component. Position. Position.
See? It is an integration. But
Because we're going back. Yeah.
don't get completely overwhelmed because it wants the z component. You only need to do your integration for just the z component. So z prime of t is e to the 3t minus 6.
Oh, okay.
And here's going to be the secret to our success. You just need to know that z of 0, so the z coordinate at t equals 0 is what? 2. That's your initial condition. So while it feels like a lot, it's only asking for the z component. We just need to remember kind of what's happening. It's saying, oh, the z component at t equals 0 is 2. So you're going to take the antiderivative.
Oh, the end.
You're going to get a plus c. You know that when you plug in t 0 for t, you should get 2 back. So we took the antiderivative, we had a plus z. I used my initial condition to solve for c, and now I can plug it back in. Of my position vector, x of t, y of t, z of t, this is the z component with respect to t. Going back, what did the question want? Determine the z component of the position vector, there it is, at t equals 3. So I just need to find z of t.
That doesn't simplify any, that's
Yeah,
just
you could maybe
simplify to 18 and 5/3. Right, okay.
Alright. So just kind of peeking through multiple choice, converting, partial derivatives. Alright. So when we come in Wednesday, I'll have practice exam 2. When we come in Friday, we'll have practice exam 3.
Oh.
Ready to take exam 2 next month.
Yes. Okay.
Alright, so one more time, remind me, what is Friday?
So environmental science exam 2, essentially, like, all the Navy options have to take.
So is this all the freshmen too?
No, it's like sophomores and